A core concept in large language models and RAG systems is the way that we encode our input. If our input is text, we use text encoding. We call it embedding. If you see this diagram, we are using the embedding in this stage where we encode all the documents that we want to retrieve, and then we encode the query of the users, and then we try to find the match between the queries and the documents so we can retrieve the right documents and generate the right replies. To understand how encoding is working, we will use this nice visualization from the Financial Times that explains the transformer, which is the core of generative AI, and it will explain us how it works. So when we get input, like text, the machine doesn't read the text. It cannot read the characters and understand them. We have to turn them into numbers so they can process it. The first step will be to take the input and parse it into words or token. For simplicity, each word is a token, but later on we're going to see that some words have multiple tokens in it and so on. We will use the unsupervised method of taking examples, many sentences, paragraphs, and documents, and let the machine try to find the context of each word, when it can appear and when it can't appear. And it will create this kind of a list that a word like ours will appear with the word work compared to the word polka that usually doesn't come with the word work. Then we take this information, these examples, and we try to calculate a vector of numbers that will represent each one of the words. It starts randomly and then it tries to guess the word. If it got it right, it will increase the weights. If it got it wrong, it will decrease the weights until it will come up with the best vector representation of a specific word, like the word work here. We will do it to many words, and we expect that words that has similar meanings, like the word sea or ocean, will have similar vectors. So most of the values of this vector are similar, but some of them are different because, again, there is some difference between those words, the same football and soccer, I and we, and so on. If we take these long vectors and try to compress them, to reduce them into 2 dimensions, we can plot them in this way and find words that are close together. For example, we can see that the word walk, run, and swim is verbs of movement will be close together, and then train, bus, and car will be close together because of their transportation meaning, and so on. But it's not enough to find a vector embedding for each word. Sometimes we have words that have multiple meanings, depends on the context. And this is why we're going to continue the process and use what we call self-attention. So we're going to see how words around the word affect them, words before, word after, and so on. And then we can find out that the words like interest can have a specific meaning in the context of liking something, like I have no interest in politics, but it can also have meaning that is related to interest rate in the context of financial institutions or banks. So overall, we can have a sentence with the same word twice in different meanings based on the context of the words around it. So if we summarize the process, we get input. The first step is tokenization. The second step is calculating embedding for each one of the words based on its meaning, based on its position, and then based on its context. Once we have this information, we can feed it as numbers into the models and start finding similarities and do the large language model generation. I want to show you another example that will give you some intuition regarding those embedding and what do they mean. So for that, we'll go to this game of the 20 questions and we'll play the online version of it. We'll try to see if the game can guess our word. The word that we'll use is C, and see if it can find it based on those questions. So it's classified as a concept. Do you hold it when you use it? No. Do you use it at night? Sometimes. Does it usually have four corners? No. Is it colorful? Depends. Is it appliance? No. Does it have a handle? No. Can you make money by selling it? No. Is it used for communication? No. Is it larger than microwave? Yes. Does it go in your mouth? No. Can liquid pass through it? Depends. Can be worn by a person? No. Does it move? Yes. Does it make a sound? Yes. Does it go over time? No. Does it stand on two legs? No. Does it bring joy to people? Yes. Does it produce heat? Depends. He's guessing that it's an ocean. So we got to, it's almost right because I thought about sea and it guessed it as an ocean. If we'll summarize what we saw, we can see that basically those questions are the different dimensions of the vector. Try to come up with questions that if we know the answer to, we can distinguish between words or guess the words that are together. So these are the dimensions, and yes, no, depends, and so on are the values. Note here that it's almost binary values, yes and no. Of course, we can do the depends and so on, but we can ignore them most of the time because we really don't know the answer for that. So overall, this is a binary vector. We will talk later how can we reduce the size of those vectors by using lower values like scalars or binary. And then at the end of the process, the nearest neighbor was discovered. Again, I thought about sea, it was ocean, but it's very close. And the process found the nearest neighbor on this vector. So I hope that you get some better intuition and understanding how embedding works, how do we calculate it, and then we can dive deeper in an example to show how can we use that to improve our RAG application.